Okay, so this is 8.33. We have this circuit, right? And basically for this circuit, we need to figure out time before zero and time after zero. And I've been messing up this many times, so I'm just gonna run through it now. I finally got it right though. But for t at before zero, we have this circuit here, right? This capacitor will be open, the inductor shorts, and the shortest path for it to go will bypass that capacitor, go through the inductor, and back to the power source. And if you take 3 divided by 150, you'll get 0.02 amps, or 20 amps, and you'll get 0 volts for the capacitor because nothing goes through it. Okay, and for t after 0, that switch is closed. And we need to find out the final value for said circuit for t after 0. Then we can find, what the general solution will be. Not general solution, but the actual value for it as it goes through time. So the inductor will short, but remember it's closed now, that switch, like so. This will open. Okay, now let's look at the paths. So this power source will flow this way. Take the shortest path back to itself. This power source will go this way, shortest path back to itself, and that way. So you have a current source coming this way and one coming down. So they're opposing each other, so we need to subtract them and find that result. So 120 is the first one, and then we need to subtract the other one, which we found earlier to be 20 milliamps, 0.02 amps. 3 divided by 150 will give you your answer. So that final value will be 100 milliamps for the inductor. Okay, so our general solution. So to find that, we know that alpha is going to be 1 over 2 RC. Wumbo is going to be 1 over root LC. And this will come out to be 10,000, 8,000. And if you plug that into your formula, negative alpha plus or minus alpha squared minus Wumbo squared, you'll get alpha, or two real solutions, will be e to the negative 16,000 will be 1, plus e to the negative 4,000 will be the other t. C1 plus C2 plus I final. What is I final? You need to be careful. It's negative 100. Because where are we finding current? We start off going down, right? That negative 100 final is going up. So that's going up. So that's opposing our original direction. We need to keep our signs in the right direction. So let's plug in our initial values. 20 is our initial. For t at 0 for the first, we'll have negative 100 plus C1 plus C2 plus the 100 over, you get 120 is equal to C1 plus C2. Now we need to find our second equation, which is dV dt is equal to negative 16,000 C1 plus negative 4,000 C2. Okay. What is dV dt? Well, let's look at this formula. Current, no. Voltage is equal to inductance times di dt. Divide L over. voltage divided by L is 0, because voltage starts off at 0. So, since that's the case, we know it's 0 is equal to negative 16,000. I know I'm going through this, but I've been getting it wrong too many times, so I am low-key sad about it. So 120 times, let's get a common denominator to simplify this. We're going to multiply the top by 16,000 to get rid of the C1. So 120 times 16,000. Okay. We know C1 is going to disappear, so we're not going to worry about it. 192 million equal to 16,000 C2 negative minus 4,000 C2 0. Add them together. We get that divided by 12,000. Get 160 is equal to C2. Plug that back into the original equation. 120 minus 160. We get C1 as negative 40. Let's plug that back into the equation. We get negative 100. What is C1? Negative 40. Minus 40. E to the negative 16,000 T plus 160 E to the negative 4,000 T milliamps is equal to that current as a function of time through that inductor. Okay, that was rushed, but let's check the It's gonna be negative 100 minus 40 plus 160 for T at 0. This is negative 140 plus 160, 20. We start at 20 milliamps, checks out for our starting value. That's good. So that means it's right.